Good morning. Welcome back. I'm Anoob Joseph. I'm a senior principal engineer at Marvell Technology. I lead the team working on network security protocols, and today I'm the maintainer of RT security and PDCP libraries in DPDK. In this session, I would like to cover PDCP, the protocol first, and then we'll proceed to see how various PDCP features can be implemented or are supported by various DPDK libraries. Following up, we'll move to Lib PDCP, that's the PDCP library in DPDK with an API walkthrough. I'll also cover the future work as well as Q&A. So first we will do a PDCP protocol overview. PDCP or Packet Data Convergence Protocol is a protocol widely used in wireless radio networks. At its core, it's a security protocol and aims at securely transferring data from lower layers to higher layers in wireless radio networks. It has support for both ciphering and authentication. So ciphering basically means encryption operation and decryption operation, and authentication is nothing but the digest generation and verification at the other end. PDCP optionally supports compression. So the compression modes are ROHC, EHC, and UDC. ROHC and EHC are the header compression algorithms, and UDC is the data compression. So here the header compression is for the payload that PDCP is taking. PDCP is a stateful protocol. It has a notion of sequence numbers. When a PDCP entity is transmitting a packet, it will assign a 32-bit sequence number. And at the receiving side, the receiving entity has to kind of arrive at the same sequence number or use the same sequence number to perform decryption and get back the original packet. It also so this sequence number at the receiving entity is also used for few other purposes such as in-order delivery, duplicate discard, retransmission, etc. Unlike protocols like IPsec, PDCP entity can communicate with another PDCP entity. Like the PDCP entity at the transmitting side can communicate with the PDCP entity at the receiving side by making use of something known as control PDUs. So these are packets, or these are PDCP packets that are generated by the PDCP layer and consumed at the PDCP layer, and it won't be going to the core network, or these packets are not coming because of an action from the upper layer. So the diagram on the slide, it's a rough summary of the tasks that PDCP protocols perform. So this is coming from the 3GPP spec, and yeah, so that's like a rough summary of how these things, how the PDCP actually operates. So where is PDCP in the wireless radio network? So so this diagram is a rough representation of where it is used in the wireless radio networks. The box on the right side, so that's marked as UV, and so this is just a simple representation. It's I mean, this is not the only way the wireless radio networks are done. It is just one of the possible layouts. So in one side we have a UE. So the UE can be thought of as a smartphone or an edge device that is trying to communicate with the remote server. So let's say we have an app on our mobile, on our smartphone, and then it is trying to communicate to the remote server. And the communication is required from the app level to the app level. The same way the TCP also will be from the UE to the remote. Yeah. So beyond IP, under or after IP, that's when we have the complete radio kind of processing happening. So there is PDCP layer, RLC, MAC, and PHY. So when a smartphone is connected to the wireless radio network, so PDCP, RLC, MAC, and PHY would be the packet will traverse through these layers, and at the radio side, all these would be traversed in the reverse order. So first it will go via PHY, MAC, RLC. So it's not, even though I represented it as one single device, so the today's 5G network is more complicated, and it's actually, so it's not just one block. It's like there is an RU which directly talks to the radio, and there is we have this DU, distributed unit, and then we have the CU also, the centralized unit. So so there also, like, there are many combinations based on what is the kind of technology that we follow. So the split can be varying based on whether you're using ORAN or there are many such variants. So, but the important idea is these RLC, MAC, PHY, these are thought about as logical blocks, and PDCP, beyond PDCP, that's where you get IP. So, and then after that, once we get back the IP packet, then it goes to the core network, and then eventually it will go to the remote server. So there are other protocols. Yesterday we saw a mention of the GTP. There is GTPU and C and all such protocols. These are for the tunneling purposes. So how the packet would traverse through the core network is what is getting decided by that. As shown in the figure, so at the radio side, once PDCP is done, then what we are getting is the original IP packet. So also do note that it is not a requirement for PDCP to have IP packet as the payload. The payload can be anything. I'm just using IP just for easier explanation, but the payload can be anything. It can even be an Ethernet packet. It can be anything that an application and the radio kind of decides between them. So PDCP doesn't have any requirement that the payload has to be IP or anything for that matter. So this is a sample flow of how a PDCP packet is constructed. So the data, the one on the box on the top, that's the data that can be the IP packet, that can be an Ethernet packet, or that can be anything that the application and the UE and the radio kind of have an agreement on. So in PDCP terminology, that is known as PDCP SDU. So SDU is service data unit, and so first the operation is the PDCP header gets added. So we will come to what exactly is the PDCP header, but let's assume that it's adding a PDCP specific header, and then so once the PDCP header and data is there, then the integrity protection is what is done first. So the PDCP header and data gets integrity protected. Basically what that means is you generate the digest and put that into the end. So the digest is a 4-byte, it's in PDCP terminology, it's MAC-I. It's a 4-byte value, and that's used for just to make sure that the packets that are going on the wire doesn't get corrupted on the way, and then we like the upper layers operate on an invalid packet. So once the MAC-I is added, then the PDCP would proceed with the ciphering operation, which is nothing but the encryption operation. So as we can see, the ciphering is applicable. It's not applicable for the PDCP header, but it is applicable for the data and MAC-I. So the portion that is encrypted is data and MAC-I. So what you see in the bottom, so that is known as PDCP PDU. That's the protocol data unit. So this is like a complete PDCP packet that gets transmitted to or that gets submitted to the below layer, and that will be received at the receiving entity. At the receiving side, the exact reverse would happen, for the decryption, decapsulation kind of option. Okay, so what we have on the slide here is a sample PDCP packet. So this is just a sample PDCP packet. So there is a field called PDCP SN. So that can actually vary. So I'll come to what it is in few moments. So that can actually vary, and because of that, the layout also can vary slightly. But then, so for one entity, the PDCP header format would be the same. So, okay. So for on top, what we have is the PDCP header, and followed by data, and then the MAC-I. So this is like a sample PDCP packet. PDCP sequence number is a 32-bit field. The sequence number is just like we have just like how we would see it in any other cases like DTLS or IPsec or any other similar protocols. So the important thing is the sequence number should not repeat for a PDCP entity. At the transmitting side, the PDCP entity is required to do an atomic increment for the entity and then assign a sequence number. This is a 32-bit sequence number. From the 32-bit sequence number, only the low few bits are put in the packet and it is sent across. So the high bits are only is more like a state. So the transmitting entity will have the high bits stored in its state, and the receiving entity will have to kind of have its own state to kind of get the original one. So at the downlink side or the receiving side, as I mentioned, the receiving entity will have to get back the original 32-bit sequence number. So it has a windowing mechanism in trying to figure out what is the exact the high bits. So yeah, that will cover sometime later. But for this discussion, so the low bits are in the packet. The high bits are coming from the stateful context that is stored only in the transmitting entity side. So the crypto operations that we discussed earlier, ciphering, authentication, all those would succeed only if the 32-bit sequence number is guessed correctly at the receiving side. If there is any mismatch in the 32-bit sequence number, then the crypto operation itself would fail. It would fail completely. Now let's proceed to the basic operations involved in PDCP and how various DPDK libraries can be used for the same. Let's start with the cryptographic features. So I've listed 3 categories. One is look-aside crypto, the other one is look-aside protocol, and then we have a hypothetical complete offload. So the complete offload mode, this doesn't exist today, but it can be added in the future if such capable devices become capable device become available. So we will start with the sequence number assignment. So as I said, at the transmitting side, the transmitting PDCP entity is required to assign an atomic sequence number, the 32-bit sequence number. If you look at the applications today that uses DPDK for PDCP, so the atomic sequence number assignment has to happen in the application. In case of look-aside crypto, it has to happen in the application. In case of look-aside protocol with PDCP, there also it has to happen. It has to be done by the application. When we are talking about the hypothetical complete offload, yeah, it can be done in the device. Again, going to the PDCP header also, for look-aside crypto, it would be added by the application. So for look-aside protocol also, it would be added by the application. And for the complete offload case, we can assume that the device will internally take care of the complete the header addition also. Going to the IV generation. So the IV or the initialization vector, that is like a fundamental building block for the cryptographic operation. So the IV is unique per packet, and it has to be constructed with the taking into account the 32-bit sequence number also. So in case of look-aside crypto, where you're offloading just the crypto operations, so the IV generation also is the responsibility of the application. And in case of look-aside protocol for PDCP, IV can be generated by the security device. Again, going to the complete offload case, so it can be fully done by the device. Ciphering and integrity protection is nothing but the crypto operations that we are all familiar with. So it can be encryption, decryption, digest generation, verification, etc. So again, for look-aside crypto, yeah, that can be completely offloaded to the device. For look-aside protocol, again, it can be completely offloaded to the device. Application doesn't have to do anything. For complete offload case, again, it can be performed by the security device. So the reason we added the complete offload is to highlight the options available on the table as we look at more capable devices and how the application would change based on the device that we have or the device on which the the application is running. So for other protocols like TLS record and IPsec, those can be like completely offloaded to the device, just like how the complete offload is done. And yeah, but for PDCP, it was decided to take a hybrid approach where the offloading is not fully done, but then it gives an offload to some extent. So one reason why it was done like that was because the PDCP sequence number is like the fundamental building block for all other features such as in-order delivery, which are more complex to be handled by the crypto device. So today's crypto device semantics are not tuned to help with this PDCP's reordering kind of mechanism or in-order delivery kind of mechanism. So these are features that needs more thinking and more evolution because before that can be done. And secondly, the acceleration of crypto itself is a huge gain and over just regular PDCP, right? So the acceleration of IB generation and having the device to have some PDCP awareness that optimizes the paths for various hardware. To summarize, DPDK provides these two options, one via RT CryptoDev and another via RT security, to accelerate the cryptographic operations. And in the future, it is possible to have one more mode that is like complete offload that could provide more acceleration. Okay. So one differentiating feature that we saw with PDCP is in-order delivery and retransmission. So this is an optional feature, but so this is actually what makes PDCP unique, and this is just like a starting point where we see how flexible and how important PDCP is to the wireless markets today. So the connection between transmitting entity and receiving entity is via various layers of radio, which could be unpredictable. So there could be packet losses, reordering, etc. But PDCP, in a sense, tries to fix up things at its own level as much as it can. So imagine that a transmitting entity is sending 10 packets. So I've drawn it, like a table which has like, which kind of reflects the window that a transmitting entity would have. And let's suppose that we are getting packets 1, 2, 3, 6, 7, 9, 10, and I've marked the packet number 6 as a late packet. So if there is no in-order delivery, and if the if the receiving entity can just do out-of-order delivery, then all these packets, they can the receiving entity can just push to the upper layer. It doesn't have to worry about any reordering or any such things. But if in-order delivery is enabled, so then what would happen is, let's say packets numbers 1, 2, and 3, that as it is received at the receiving side, it will be pushed to the application. But let's suppose we are getting packet number 7 as the next packet. So then obviously packets 4 and 5 are missing. So the PDCP layer detects that there is a packet missing, and it starts setting the various state variables. So the RX deliv, RX reord, RX next, these are the state variables that are used to track this window of packets that are in the window, out of window, etc. So RX reord is the state variable that represents the packet that was received out of order at first. So let's consider that the packet number 7 received first. So the RX reord will get set to that, and RX next is more like the upper bound of the window, like what is the highest sequence number that the PDCP entity has seen. So if only packet number 7 is received, yeah, then RX next would be at the same point as RX reord. But let's say after that it receives packet numbers 9 and 10, then the RX next would move to the front. But RX reord will stay there. RX deliv will also stay there. So basically what happens is, so the RX deliv would move only if you get all the packets. So until packet number 4 is received, it will just stay there. So RX deliv actually acts as the lower bound for the acceptance window of PDCP. Okay, so now that we have seen the PDCP's window mechanism, so what options are there in DPDK to implement the same? So we make use of, or we can make use of RT bitmap and RT reorder libraries for implementing this reorder window. So so the bitmap kind of gives application an idea of or application can use it for tracking like which all packets are received, etc. And the RT reorder library can be actually used to buffer the packets. But so once we did a deep dive into RT reorder, that's when we realized that there are few shortcomings in RT reorder library, specifically around how the RX deliv and all is being done for PDCP. So RT reorder is so to begin with, RT reorder was a very simple library. I mean, it's a very optimized library. It's built for performance. But the sole intention with the RT reorder library was we can give a number of packets, and then we can have the RT reorder library order it, and then the application can drain packets from the RT reorder library. With PDCP, the draining became more complex. So there were two major limitations that we saw. So the first one is RT reorder library would return n number of buffers in order only. So let's suppose in this example, so let's say instead of, let's say we have 1, 2, 3 packets, and we don't have packet number 2. So we push packet numbers 1 and 3 and to reorder library. It would never drain 3 if 2 is not available. So it's basically the reorder library would not move until all the packets are received. So this matches how PDCP expects, but PDCP has other mechanism to kind of have the window progress. So that is not supported by reorder library. So this was one major item that we saw. The second is imagine we are going to push packets 6, 7, 9, 10, whatever that came as reordered here, right? So once we push packets 6, 7, 9, and 10, so reorder treats packet number 6 as the minimum sequence number. So in this case, what we are actually expecting is packet numbers 4 and 5. But the reorder library will reject, saying that these are like out of window. So these were the two major gaps that we saw, and then there were a few other optimizations also that, or some other shortcomings that we saw and we addressed. So one was regarding the memory footprint of this RT reorder context kind of. So for smaller window sizes, we can just assume that these many mbuffs and these many, it is possible for the application to kind of allocate some memory, and it's possible that we get into the right range. But with PDCP, the window sizes can go to like 2 power 11 or 2 power 17 kind of windows. So the number of packets that you have to that the application is required to cache becomes just it becomes huge, and then the memory footprint has to be calculated precisely and added. Otherwise, it's like so if the application is like, okay, if it's just assuming for 2 power 18, it won't be efficient for something like a smaller window size. So all such problems were there. So that we added as an enhancement. So that's also one of the other API that we added. So for this, let's get back to this discussion. So there were two major problems that we saw. So one was regarding the drain mechanism, where if there are any gaps in between, the application was not able to drain out those packets. And the second one was regarding the setting the minimum sequence number. So the application would want to set a sequence number that is lower than the sequence numbers that are actually pushed. So in order to address these two problems, so we added two APIs. So yeah, I hope it's visible. So the first one is RT reorder drain up to sequence number. So the RT reorder drain up to sequence number, so that is that allows the application to drain up to a sequence number, irrespective of whether there is a gap or whether it's continuous, or doesn't matter. So it gives the application the flexibility to drain up to a specific sequence number. So if you look at the window, right, as in, so let's say DPDK application decides that it wants to drain from let's say packet number drain up to packet number 7. So then it can just call this API with the sequence number as 8, I believe. So the reorder library will give back all the packets. And the second API is to set the min sequence number. So as I mentioned earlier, so this is just to make sure that the missing packets get accepted. Okay. Yeah, timer is another important feature. So earlier we saw if RxDeliv is at a point and if the packet is missing, so would that mean PDCP processing would stop at that point? So based on the way I explained, it would look like PDCP processing would stop the moment there is a packet loss. But if it was working like that, then we wouldn't have had any of the seamless experience that we have with our phones today. So how would PDCP kind of address this particular case? So the timers are used to actually help the window progress. So when PDCP entity sees that a particular packet is missing, so then the Rx reord the state variables get set. Rx reord will get set to something, and then as we discussed it, the packet would get pushed to RT reorder library, etc., etc. At the same time, there is a timer that is getting started. That is known as T reordering. So the timer would get enabled, would get started, and then if the packet arrives, like if all the packets till that point arrives before the timer expires, so then PDCP entity can stop the timer and then continue. If the packets are not received on time, then what would happen is the PDCP entity is required to push all the packets that it has cached to the upper layer, and then it has to update all the state variables accordingly. So this is regarding the T reordering timer. There is a similar timer at the transmitting entity also. So at the transmitting entity, so there is something known as a discard timer. So from PDCP's point of view, again, I think, this is also another optional feature. There is something known as retransmission, where one PDCP entity is sending packets to the other end, and then the other end guy will say, okay, I didn't receive these packets. So then the transmitting PDCP entity can actually retransmit the packet. So if we want to do that, so we will have to cache the original packets. Then only the retransmission would work. So PDCP layer allows for a retransmission, and there also it is like the DPDK applications cannot cache the packets for so long, right? So there is a concept of a timer where the packets would be cached only for a specified time duration. So that's something known as a discard timer. Okay, going back to what does DPDK give to support these cases? So for timers, there are two options. One is RT timer, and there is RT event-based timer. So RT event-based timers are the hardware timers, and so RT timers are the software-based ones. So RT event-based ones require special hardware that can do it, and for RT timers, the regular RT timer we can use on any platform. Okay, let's go to Lib PDCP. So why do we need Lib PDCP? So PDCP is a protocol that requires many features, many of which are already available. I talked about RT bitmap, I talked about RT reorder, and CryptoDev, security device. So there is like a lot of requirements from PDCP on DPDK, and all of which is there in DPDK. And the thing is, there are overlapping features. So just now I talked about RT timer and RT event. The same way there is overlap for RT CryptoDev and RT security. So if there is a difference in the capability between devices, so then the application would need to kind of adapt to that. And then so it's always beneficial to use the platforms which have like more offloads. But then if the application is written for such a platform, then it would become harder for that application to move to another platform, even though they're all on top of DPDK. So this is a table that we saw earlier. So I had added look-aside crypto, look-aside protocol, and complete offload. So where is Lib PDCP coming? So Lib PDCP forms another category or another set of APIs where application can directly talk to Lib PDCP. And following is, so if you see in all the boxes I have written Lib PDCP plus device. So what that means is the abstraction is completely done by Lib PDCP. So if Lib PDCP is working with a device that is only doing look-aside crypto, then it can kind of so whatever device is not doing, Lib PDCP can internally do the same, and then from the application's point of view, it would just look like offloading the complete thing. So from the application's point of view, it doesn't have to care about the device. It doesn't have to worry about APIs changing or anything. All it needs to do is just stick to the Lib PDCP APIs. So this is the spirit under which we try to add Lib PDCP. And so earlier I also said this complete offload, it doesn't exist today. So tomorrow a device is there with not the complete offload, but some more offloads than what is existing today. So then we don't need to have the application changing. We can have the application just using Lib PDCP, and the required handling can be just added in the Lib PDCP, and the application would just stay the same. So I'll just go through the control path API. So yeah, so these establish, release, suspend, these are the terminologies from the 3GPP spec. We have tried to follow whatever is mentioned in the 3GPP spec. So the establish is it's all about creating a session. So one key differentiator here is so when the application calls an established PDCP entity, the actual session, the session on the RT crypto device or an RT security device, these will be done by the Lib PDCP itself, rather than having the application to create something and give. This is because PDCP has a concept of changing the keys on the fly. So we can have a RT crypto session created when we do the establish, but it has a procedure for something known as a re-establish where the keys would get changed. So then we didn't want the application to kind of create another session and do all that business. So the abstraction we are doing in the Lib PDCP itself. So release and suspend, yeah, they also follow the same procedure as described in the specification. So since, as we discussed, so PDCP can cache packets, it can store packets that are used for the retransmission purposes or in-order delivery kind of purposes. So these APIs also allow packets to be returned. So if you can see, both the APIs will have an argument struct RT mbuf that pointer out mbuf, out MB array. So that's used to give back the packets that the PDCP entity has cached. So at the bottom we have a PDCP entity conf. That's like so I've trimmed down all the comments. So if you go to rtpdcp.h, we can see the complete description of what each field means. And so yeah, so I don't intend to cover everything because there are like small features that could take time. But the whole idea is all these are taken care in the in Lib PDCP. So we can just enable one feature, start using it. Okay, coming to the data path. Yeah, again, it would start with receiving a packet. So how the application receives a packet, yeah, that's up to the application. So that can be like very device specific things. So that's not something that Lib PDCP are trying to address today. So the packets can arrive from somewhere, but the moment you have an mbuf, yeah, so that's when the actual that's when Lib PDCP actually comes into picture. So first we go for PDCP preprocess. So PDCP preprocess is the one that allocates something known as a crypto op that is used for the crypto operation, and so yeah, just like that. Yeah, it also prepares IV when we are doing the look-aside crypto mode. And yeah, these are the everything that is required before doing the crypto operation would be done in the pre-process stage. And after that, the packets get submitted to CryptoDev enqueue, and then the packets get returned by the CryptoDev via CryptoDev dequeue. After that, PDCP post-processing is performed. So post-processing is where the reordering thing would happen. Like many of the features that we talked about would happen. So uh, yeah. So for receiving entity, yeah, this particular API, since it would perform the in-order delivery functionality, it can take a number of packets and it can return a totally different X number of packets. So we can enqueue n number of packets and we can get back a totally different X number of packets. So that's how the post-processing API would work. And the API is written such that application can get back those packets, etc. So once that is done, yeah, transmit out the buffers. So this is like a regular flow, or rather a very simple flow. Okay. So earlier we discussed about how PDCP entities at receiving side and the transmitting side, how they can talk to each other. So how is that possible? So that's possible via something known as a control PDU. So control PDUs are just packets that the PDCP entity creates and then populates, sends it across. The other side will receive it and then do the processing, and then it doesn't give to anyone else. It consumes and frees the packet. So the other packets get originated from the upper layer, and then at the receiving side, it's like again it pushed to the upper layer. So this API that's shown, so this is used to create the control PDU. So the control PDU can be something like a status message, like so status message is like it will have a again it's mentioned in the 3GPP spec. So the status message is something like it will have a bitmap of which all packets are arrived, and it will have the state variable such that the other side can actually see which all packets were received. So yeah, and just like that, I earlier mentioned about some of the compression algorithms like ROHC, EHC, and UDC. Some of it requires something known as a feedback. So from the one side, it will send a feedback across to the other side, and yeah, that way these guys keep it in sync. Okay, so timer. Earlier we discussed about the timer. So this was a major challenge when we started integrating. So this was because the timer is actually started and stopped at the PDCP level. So earlier we saw that the timer would get started or stopped when as part of the post processing. So Lib PDCP is required to call an API to start the timer and stop the timer. But the actual timer can be different. So as I said earlier, right, there are hardware timers, there are software timers, and if Lib PDCP is sticking to one, then basically Lib PDCP becomes usable only if that particular device is available. So that we didn't want to make that choice. So because of that, the design choice was to have this application register the callbacks for starting and stopping the timers. So the application can just use this start and stop timer per entity it can configure, and then PDCP, as it processes the packet and sees that there is reordering happening, it can start the timer. When it sees that the packets have arrived, it can stop the timer, and it can do whatever it wants. But the actual timer expiry, when it happens, so the timer expiry that will be received either via RT event or RT timer, right? So that will be that event will reach the application. So then the application has to call this API RT-PDCP T reordering expiry handle, so that the what is the processing that is required for such cases, so it will be completely done. So what's available today? So the APIs were added in DPDK 2307. So, and we have added like multiple features after that. Some of this reordering and all was added in the later releases. So the unit tests were also added at the from whenever there was a feature that was introduced, we made sure that unit tests were also added. So for all the features that Lib PDCP supports today, unit tests are available in the standard DPDK test. So there are few unit tests where we test all the packet sizes that are required for PDCP, like 1 to 9K or something. So there are tests that actually test for every single packet size, and yeah, so there are few test cases like that for all the algorithms. So we have verified Lib PDCP with both crypto CN10K PMD and software PMD. So not just crypto CN10K, there are a few other internal PMDs, not internal, there are a few other PMDs also that we have. And so we have verified with all the Marvell PMDs and the software PMDs that we have access to. So okay, and we had a very good team from Marvell to work on this project. So Akhil and Jaren were involved in defining the architecture and code reviews. Akash, Kiran, and Volodymyr helped with the implementation of Lib PDCP as well as addition of various unit test cases. Special mention to Vladimir because he took up all the changes related to RT reorder, and so currently he has he is the maintainer of RT reorder library. He volunteered for doing that, and yeah, special thanks to him. Also, we took a lot of inspiration from RT IPsec library, which solves a similar kind of problem for IPsec. We had tried to make Lib PDCP similar to Lib IPsec so that so wherever possible, so that all protocol libraries in DPDK would follow the same theme. Special thanks to Konstantin and the complete team who added Lib IPsec. So future work, so we have certain features that are still work in progress, like this retransmission control PDU handling. So yeah, we are looking at some of the optimized paths, and yeah, so these are optional features which would take some time, and we are in the process of getting it done. And a performance application is in our list, enhancing RT security to support more capable devices. So there are a few other items that we have, and yeah, from the community, yeah, all contributions are welcome, and yeah, so yeah, that's about it. So yeah, I think we'll go for Q&A.
Any questions at all?
Thank you, Anoob, for the presentation. I have two small queries. One is on the RT reorder library part, and second one is on the RT timer part that you presented. The figure, the other one, please. Yes. We already had a RT reorder library with certain way of working.
Yeah.
From what I heard when you presented, certain things were not as similar as what the PDCP processing layer required. Hence, it was modified.
Yeah.
So are these modified changes put back into RT reorder? Yes. If yes, did we add new set of APIs, or we extended the APIs? Can you please retouch on that?
Yeah. So none of the functionality is broken. Like whatever was existing, we didn't touch. So when we analyze the code, we didn't have to modify any of the APIs. So we added 2 APIs. So this is just about, one is about setting an internal state. Okay, so that is just, so regular RT reorder without calling this API would behave in a certain way. So that we didn't change. So this API, so the second API is just to set an internal state. Okay, that doesn't affect the behavior for anyone who is using
RT
reorder. The first one, again, so there is an RT reorder drain. Okay, that we didn't touch, because that gives application. So that is useful for many other protocols, and we are not saying that that's not the right thing. So with this API, we are giving another option for applications to drain in a different way.
Correct.
Yeah.
So the RT reorder init, are you enabling that state in RT reorder init?
No. It's just like RT reorder init is exactly the same.
Okay.
So that was a discussion that I believe we had in the community.
Yes.
Yeah. And it was decided that we'll have one more API to control it, the min sequence number.
Okay, so it is added as a separate API, not part of RT init. Okay, thank you.
Yeah, not modifying any of the RT reorder APIs, but all these are part of RT reorder standard upstream.
Okay, the second one was with regard to RT timer part, especially the event timer, hardware timer.
Yeah.
I was trying to understand from the RLC to the PDCP, then to the app layer. There are two parts. One is the app giving the data of the payloads, like what we discussed. And other one is the PDCP layer giving to the thing. So I understand when you receive from the RLC part, the PDCP timer coming into play, and at exit of the timer, it hands over through callback. That part is clear. But when you are the app, like when you are the eNode B and all, when you want to transmit out, you are giving the PDU. So how does the out of order or missing payload comes into play?
Yeah. So
Thank you.
So what you described is for the T reordering thing. Okay. So yeah. So so there are two timers. One is T reordering, that is in play for the receiving entity where the missing packets, etc. So what if there is a missing packet? So we talked about it will have the window and all that thing. So the PDCP has a mechanism where the receiving entity will say, okay, hey, I didn't get this packet. Give me that packet. So it can send a control packet, control PDU, and the other guy has to send it again. Okay. So how does that send it again? Because it has to cache these packets, right? Can it infinitely cache the packet? Yeah. So there is something known as a discard timer there. Okay. So the thing is, so the PDCP, the 3GPP spec calls it as a discard timer, but like this is something that we are internally discussing. So should it be a proper discard timer, or do we just need a timestamp, right? So I mean, I think maybe I'm going into the details, but the idea is, so the discard timer is for the transmitting entity, so that it doesn't cache the packets for too long. Hope am I clear, or should I clarify again? So maybe I'll just do, okay. Maybe I'll give an attempt again. Okay. So there are two timers. One is a T reordering timer, that's for the receiving side, and there is a discard timer for the transmitting side. So the transmitting side, when it transmits a packet, it sends it out. It shouldn't just free the packet. It should hold the original packet, and it will have an expiry. So when that discard timer expires, that's when we can free the packets to the pool. Yeah. So these are the two timers.
Okay, one more question about timers. Do you think it would be possible to automatically select the best timer?
Yeah. Oh, okay.
Because you are asking the application to choose the timer.
Yeah, just choose. Okay. So the thing is, the expectation is application has to choose the timer, and then it has to configure the timer, because the idea is, let's say if you want to configure RT event versus an RT timer, right? The way it happens is different. So if we are using RT event, then we have to configure the RT event dev, then we have to configure the adapters, etc. So we didn't want Lib PDCP to kind of get into all that nitty-gritty. But so for the application's benefit, we have added all this in the unit test. So today there is a unit test where there is RT which uses RT timer. There is unit test which uses RT event based timer. So these are like standard things, and we didn't want Lib PDCP to kind of make decisions for the application.
Okay, makes sense. I would like to talk about what you name complete offload.
Yeah.
We're talking about inline, right? Inline offload.
Okay, so inline is the next thing that we have to. Okay.
What's the difference between inline and complete offload?
Yeah, so complete offload, I'm talking about look-aside protocol itself, where the crypto dev is actually submitting to the application is actually submitting to crypto dev. But in the long run, I do see that this can evolve into an inline protocol. But that's where we have to really get into the nitty-gritty. So yesterday we discussed about how inline IPsec actually depends on or has problems with IP fragmentation. So if you look at PDCP's thing, there is like RLC, MAC, PHY and all. So that is something that in DPDK, we don't have those established ways of dealing with those devices. So that's the reason we are not, or I didn't talk about inline protocol, but it's very much doable. The moment we add the complete offload for crypto dev, the same thing will come for inline also.
Okay. I'm not sure to understand why in look-aside protocol we are not managing every part, I mean PDCP header and sequence number. They are not managed in look-aside protocol here.
Okay, so your question is, why is application managing the sequence number in case of that? That's how the spec is today. So the problem is, if the sequence number moves to device, right? As in, if the sequence number assignment should be done by the device, then there is like a lot of state that it has to handle internally. So yeah, so that is something that we are looking to improve. So there are practical challenges, or it requires more device capabilities. And like I had a look back at the PPT when the RT PDCP was introduced, and this particular problem was discussed at length. So there were two approaches that was discussed at that point of time, and it was described that, okay, if we are going for a complete offload, that requires more capabilities from the hardware, and even the CryptoDev APIs are not may not be that suitable. So there are challenges there. So today, what we have with RT security, the PDCP offload with RT security requires application to do the sequence number assignment.
Okay. And last question. When you describe the flow in the Lib PDCP,
Datapath.
yeah, this one, exactly. So the application is starting process, etc., getting mbuff, but it doesn't apply if we implement inline protocol, right?
Yeah. So the way it would happen is the pre-process and the CryptoDev so maybe the first 4 points won't become applicable. Okay. And then the post-process will become applicable.
Okay.
Yeah, that's so. Yeah, that's the flow that we have to really map through and see. But I really think that's how it would happen. The first 4, when it is inline, the first 4 would go away for the receiving packet. And for the transmitting side, again, the post-process and the transmit out mbuff will be completely done in the hardware. So, yeah, so.
Yeah. Okay, thank you.
Thank you.
Sorry, I have one small question regarding PDCP with the test crypto perf. Since last time when I developed ASGCM with Melox 5 PMD, in fact, I found that something was not fully supported in test crypto perf. So I just want to know regarding this API, has everything been supported? For example, in test of crypto perf, we have performance, we have throughput, verify, and such model. So I just want to know if that has been supported. Okay.
So the CryptoPerf is mostly about getting the raw performance of the hardware devices, right? Yes, yes. So RT PDCP, these APIs may not fit right there, and we are not targeting that because there are practical problems when we plug in stateful protocols to DPDK test CryptoPerf, and it's not designed for that. But we think that what we are doing is we are trying to add a separate application, something like an L2 forward PDCP kind of application. So, that's the theme that we are internally taking, but that's not fully done. That's in the pipeline. Yeah. So this is about the performance side. But for the unit test, it covers everything. So whatever Lib PDCP supports today for so all that is covered by unit test. So if you want to verify the functionality, yeah, unit tests are the first place to look at.
Okay, thank you. I see.
Thank you.
Any other question? No. Thank you, Anoob.
Thank you.